Welcome to today's Explainer class. Grab your notes because we are diving straight into a high-yield exam review for Chapter 5, Chemical Bonding. Think of me as your personal chemistry professor for the next little while. We're going to break down the exact concepts you need to know from pages 73 to 94 so you can absolutely crush your upcoming board exams. All right, here's our class syllabus for today. We'll be covering 1. Why do atoms bond? 2. Types of chemical bonds. 3. Drawing electron dot structures. 4. Bond properties and uses. 5. Board exam practice problems. And finally, 6. Exam tips and mistakes. Let's get right into it. Section 1. Why do atoms bond? The quest for stability. Now, you might be wondering, why do atoms even bother interacting? Well, most atoms in the universe are just naturally reactive and restless, and bonding is basically their way of finally relaxing. Think of atoms like avid collectors trying to complete a super rare set of trading cards. The Octet Rule is this natural drive to collect exactly 8 electrons in the outer or valence shell. Getting this complete set gives the atom the ultimate stability, literally the exact same electronic configuration as a noble gas. And the Duplet Rule. It's the exact same idea, but for smaller atoms like hydrogen and lithium. They only need a set of 2 electrons to be perfectly stable, much like helium. So to reach this super stable setup, atoms have different strategies based on their inherent nature. Electropositive elements, which are mostly our metals, are kind of like generous collectors. They actually tend to lose their outermost electrons to find stability, forming positively charged ions. On the flip side, electronegative elements, our nonmetals, are the takers. They have a really high electron affinity and eagerly gain electrons to complete their sets. This back and forth dynamic is the very foundation of how all different types of bonds form. Moving right along to Section 2, Types of Chemical Bonds. Giving, taking, and sharing. Examiners absolutely love this section, so you'll want to pay close attention here. Let's go back to our trading cards analogy. An ionic bond is a permanent giveaway. A metal completely transfers its electron to a nonmetal. Simple as that. Covalent bonds, though, are more like sharing a rare card with a friend so you can complete both of your sets at the exact same time. Nonpolar means totally equal sharing, while polar is unequal sharing. Then we have the coordinate covalent bond, where one very generous atom donates the entire pair for sharing. And metallic bonds? That's just a massive, beautiful sea of free-floating electrons. Take a look at this. Let's zoom in on a classic covalent bond. Notice how those overlapping circles so elegantly illustrate the sharing of valence electrons between 2 hydrogen atoms. This shared pair right in the middle creates a very strong electrostatic attraction. It firmly holds the 2 positive atomic nuclei together, forming a super stable diatomic H2 molecule. Now, if you're taking notes, and you really should be, put a massive star next to this concept. This is the formation of the ammonium ion, NH4+, via a coordinate covalent bond. It is a classic board exam question. Notice how the ammonia molecule, specifically the nitrogen atom, has a lone pair of electrons just sitting there. It donates this entire pair to the hydrogen ion, which comes to the table with literally no electrons of its own. Once they're bonded, it is entirely impossible to distinguish the origin of those shared electrons. It's a really neat trick of nature. All right, Section 3, Drawing Electron Dot Structures, the visual application. Look, if drawing these structures has ever tripped you up, take a deep breath, because the textbook gives us a totally foolproof 3-step problem-solving strategy. Step 1, decide the central atom. This is the guy that needs to form the most bonds. Step 2, arrange the other atoms around it and connect them with a single bond, representing one electron with a cross and the other with a dot. Step 3, count them up. Just double check that every single atom in the arrangement fully satisfies either the octet or duplet rule. Let's actually see this in action with methane, CH4, and water, H2O. Carbon and oxygen are our central atoms here. Notice how we systematically use dots for the central atom's electrons and crosses for the hydrogens. By methodically following our 3 steps, we can clearly map out these single covalent bonds, ensuring carbon gets its 8, oxygen gets its 8, and every single hydrogen gets its 2. Boom. Perfect stability. Which brings us to Section 4, Bond Properties and Uses, the physical world. So how do all these invisible microscopic bonds actually dictate the physical world around us? Well, the melting and boiling points of these compounds are guaranteed multiple-choice exam material. Notice the stark difference here. Water, which is a covalent compound, boils at 100 degrees Celsius, but sodium chloride, an ionic compound, requires a massive 1465 degrees just to boil. Why? Because breaking the incredibly strong electrostatic forces between those rigidly packed, oppositely charged ions in an ionic lattice requires a tremendous amount of heat energy. Speaking of forces, we absolutely have to talk about a very special intermolecular interaction, hydrogen bonding. When highly electron-deficient hydrogen gets near a very electronegative atom like oxygen, you get the strong dipole-dipole interaction. It's the whole reason water has such unique, life-giving properties. And, as the textbook fascinatingly points out, it's what gives epoxy resins their incredible adhesive strength, literally strong enough to hold modern aircraft and spacecraft together. No way, right? But it's true. Examiners also love to ask about giant structures, so let's do a rapid-fire rundown. Graphite and diamond are both made of pure carbon, but their bonding changes everything about them. Graphite's 2D layered structure makes it a soft, slippery conductor. Diamond's massive 3D covalent network makes it incredibly hard, which is perfect for industrial cutting tools. And metals, that sea of delocalized electrons allows the positive ions to slide past one another without breaking, making them super malleable and highly conductive. Okay, Section 5, Board Exam Practice Problems. Let's test your knowledge. All right, class, pop quiz time. Let's tackle 3 problems pulled directly from the textbook's concept assessment to see if you're really ready for the boards. Practice problem 1. Look at this list: KCl, AlCl3, MgF2, NaF, and NaBr. Which ones feature ionic bonds? Take a second to really look at the elements involved. Think back to our electropositive and electronegative rules from earlier. Moving on to practice problem 2, I want you to visualize and mentally draw the electron cross and dot structure for the ammonia molecule, NH3. Try to apply that 3-step strategy we just talked about. Who is the central atom here, and how many valence electrons does nitrogen actually have? And finally, practice problem 3. Explain the formation of a covalent bond between 2 non-metallic elements. This is your classic long-form question. Think about how you'd structure your descriptive answer to make absolutely sure the examiner gives you full marks. Okay, let's see how you did. For question 1, it's actually a bit of a trick. All of them are ionic because every single one pairs an electropositive metal with an electronegative non-metal. Huge props if you caught that. For NH3, nitrogen sits right in the center with its 5 valence electrons. It shares 3 with the hydrogens, leaving 1 distinct lone pair right at the top. And for that long covalent formation question, you'd want to clearly define mutual sharing, mention that electrostatic attraction holds the nuclei together, and probably sketch that overlapping H2 diagram we saw earlier. Finally, Section 6, Exam Tips and Mistakes. Maximizing your score. Lean in for this part, seriously, because this is where you separate a B+ from a perfect score. Here is exactly where the examiner is trying to trick you. First, when drawing covalent diagrams, keep your crosses and dots distinctly assigned to specific atoms. Do not just make them up randomly. Second, when drawing complex ions like ammonium, students constantly forget to draw the square brackets and the little positive charge on the outside. Do not throw away that easy mark. Finally, do not mix up your definitions. Polar covalent means unequal sharing of electrons. When you inevitably get hit with one of those massive long-form questions, here is your bulletproof strategy. Please, whatever you do, do not write a giant, unreadable block of text. Start with a crisp, clear definition. Always include a labeled diagram, even if they don't explicitly ask for one. It proves you understand the concept visually. Throw in a real-world example, and format your answer using bullet points to make it incredibly easy for the examiner to just hand you those points. We've covered a ton of ground today, from the basic atomic urge for stability to the complex structures of diamonds and even the mechanics of spacecraft adhesives. But I'm going to leave you with this provocative thought to chew on. If the intermolecular forces of hydrogen bonds are technically considered weak compared to actual covalent bonds, how in the world do they manage to hold the precise DNA double helix in our bodies and the tough epoxy resins of spaceships together so perfectly? Keep exploring, keep questioning the world around you, and best of luck on your board exams. You are going to do absolutely great.